Cool. Hi there. Thanks for coming. If you're here for the SciPy talk, this is not it. So I'm sorry, this is a last-minute change in the schedule. But you're also not allowed to leave now because I already started talking. So just sit down. It's going to be asyncio. It's going to be fine. Before we begin, trans rights are human rights. I'm against bigotry and any legislation that limits people from being their true selves. My name is Łukasz Langa. I'm the CPython developer in residence. I'm a release manager of some ancient versions of Python. We will not be talking about those today. We're going to be talking about 3.11 and the future. It's a great role, kind of, you know, my dream to be able to work on Python full time. I'm very grateful to Meta to just made it available for me to do it for another year, so thanks to them. But now we're not going to be talking about happy things, we're going to be talking about problems. So what is our problem? Everybody says Python is slow. And Python is slow in different ways to any user of Python, because it really matters what you're trying to do with it, and you know how you observe that it's not as efficient as you would like. So we're not going to be talking today about the startup time of Python. We're not going to be talking about the sheer crunching, number crunching power of Python. Instead, what we're going to be talking about is concurrent data ingestion that ends up with parallel data processing. So, you know, kind of, I use the word concurrent there, and I use the word parallel. They sort of seem the same, but they're not. You know, concurrency is the ability for us to deal with many things at the same time, even if we are only able to do one thing at a time. And parallelism is actually doing many things at once. A good analogy for this is that, you know, one bartender can prepare one beverage at a time, but they can still look after several customers, right? But if you want them to be able to prepare multiple beverages at a time, now you need many of them, right? So concurrency, being able to serve multiple customers, and parallelism, being able to prepare multiple drinks at the same time. So today, we're talking about both of those things. So in particular, some of the archetypes of data processing that you're going to see that are especially hit with the problem that we're going to be talking about today are data syncs. So data syncs are either, you know, kind of data that you're accepting from somebody periodically, or, you know, just request-based, where you're mostly just ingesting them to a database for further analysis later on that is not part of your system on its own, right? So it's either you pulling something on your own, or you being pushed data. Then you have the web, right? So request response. Obviously, there's more than HTTP that does this, but everybody thinks of HTTP when they think about requests and responses. So here, the crucial thing is the ability for us to serve multiple clients at the same time and give them responses in sensible time to each of them. And then you have MapReduce. You know, back in my day, 20 years ago, like it was like all the rage. But now it's still super useful. Like it lets us deal with data that are too big to be handled by a single thread, single process, or even a single machine. So what you do is you essentially split, process data, and then combine the result, right? So that is essentially the most kind of interesting of those three, because it doesn't have any well, distractions for us. We can focus on essentially making sure that we can utilize our hardware to its full potential. So, you know, let's talk about this kind of processing and how Python can be used in ways that are not slow and not frustrating. So first, let me give you an example. This is a slide from an internal presentation I did at Facebook some 7 years ago now. We observed a weird thing in our service where there were like 2 threads that we were working with, and one of them had what we expressed to be a CPU leak. There is no such a thing, but it's how we saw things happen. There was a periodic thing that the green thread was supposed to do, but for whatever reason, it was doing it increasingly rarely. And we were really confused by it because it wasn't that the task was taking longer. No, it was still the same thing, only it just took increasing amounts of time for us to wait until it actually happened, which was really frustrating. And it was a little confusing also to find out what is happening, because we, we used PDB, nothing was really showing up. We used cProfile, nothing was really obvious there, since cProfile doesn't deal with multiple threads easily, so we could only observe R2. And long story short, it turned out that, yeah, there was a third one. There was a shared library, ironically used for performance metrics, where somebody made a change, where they were like, no, we cannot send so much data over the network anymore just for performance metrics, so we're just going to aggregate them in the process. And because of a slight misunderstanding in how Python works, they were just accruing data and never throwing it away, which meant that the third thread was in fact taking longer and longer to complete. And why would that even matter for us? Why would that matter for the blue and the green thread? Well, because of the global interpreter lock. So a feature of Python that we had from the day that Python added threading, and we still have it. There are obviously changes to it. We can improve on it, but it's what we have today, right? Even if your computer has multiple processors or has multiple cores on a single processor, outside of a few tricks that we can do, only one thread of Python will execute at a given moment in time. And obviously, that seems like a problem that should be solved. So there are multiple attempts to address this. The first serious one that was successful was the Gilectomy in 2016, where Larry Hastings removed the GIL, and Python still continued to work. However, it wasn't really that fast anymore, because, ironically, having one lock for the entire interpreter to protect its data structures with is really efficient. So if you remove this one lock and replace it with many locks, it's no longer that quick. And moreover, Larry was at the time unable to make it work in ways where if you add cores to your problem, it scales up kind of linearly. You would expect this, right? If you have a problem that is, crunched with one thread, it should take more time than one that, you use 4 threads for. But this is not what we observed. Like, pretty quickly, it tapered off, and adding more cores, more threads to your program, they didn't do anything actually anymore. So this is why the problem stayed, and it was kind of not addressed until Sam Gross from Meta came around and removed the GIL again in 3.9. And this time he made some more extensive changes such that Python could scale. It was still slower in a single thread, because the truth of the matter that a single lock is faster than many locks, this is really hard to, kind of jump through, but it did scale. So if you put 4 cores on a problem, it would be close to 4 times faster than just putting 1 on the same problem. So that's cool. And there's a PEP open. Why is it accepted? Well, because it turns out a lot of Python programmers like you depend on the implicit behavior that having a global interpreter lock gives you. There is a lot of Python code that is not thread safe, because that was never really an issue. Even if there were multiple threads, they were effectively serialized. So, it is not an easy decision for the steering council to make whether we should break this in the name of scalability. Well, so I'll leave that problem to them, and we're going to talk about the GIL and what we can do with having the GIL, right? So, like, just even if we removed it, right? In the best case scenario, the most popular version of Python today is 3.8, right? Like, while we are on the brink of 3.12 beta 1. So it suggests to me that even if we added even if we removed the GIL from 3.13, that would be released October 2024. Add 5 years to that, well, you would be able to enjoy the GIL-less Python in 2030. So maybe let's still stay on the talk, because it's relevant what I'm about to say. So what are we going to do today? It was this kind of epiphany a long time ago that somebody had that, it is a waste of time to wait on an external resource if you need multiple resources to be available to you? What if we could, instead of waiting for one, and then when it's complete, waiting another time for another one, sort of move things around and just say, I'm interested in all of those. Tell me as soon as any is available. So this is essentially the basis of async IO. We have an event loop, and in that loop, we're asking, do you have anything for me? And we can subscribe to multiple things that we want to be ready, right? So like connections and so on and so on. So this is a view of a single request and response. But the real matter, like the real server that you have, will look more like this. So you have a single, kind of request being served, but there's going to be many requests served and responses sent back at the same time. And this is the basis of Node.js. This is the basis of Nginx. Like it's, this asynchronous programming is very popular kind of across the board. It is kind of agreed upon that it is the most efficient way to do this. It's wasteful to waste an entire thread and its memory for just waiting on things. So this is what async IO does. It essentially allows us to maximize the usage of a single thread. If you want to use many threads, just launch multiple processes. You have multiple cores. This is how you solve it, right? And then we handle I/O asynchronously, right? So we just subscribe to changes, and as they happen, we are notified. And finally, we can write concurrent code in Python using coroutines. I'm not going to be able to really just give you a primer on this today. So let's just say async IO is nice for IO, but it's also nice for orchestrating processing of actual computation. For example, Black, the auto-formatter, doesn't have any networking built in, but it is using async IO to make it possible for you to auto-format multiple files in a directory at the same time. As long as you have enough cores, it will use async IO to orchestrate this. So we're going to be talking about how to use this for, data science-y things today. I don't have time to do a primer on async IO, so just, kind of bear with me that there are async functions, so those async defs, and they have awaits in them. And awaits are the things that, kind of denote IO. So things can happen that can take time, and we're waiting for them. The nice thing about this is that it reads from top to bottom. In the example here, we're awaiting on a download of file 1, and only after that completes, we're awaiting for file 2 to download, and only after that completes, we're awaiting for file 3 to download. So those things are still linear. We can read it from top to bottom. No kind of callback nonsense, no callback confusion. But we can do some magic there, and with the help of, say, async IO gather, we can make those things happen at the same time. So that's pretty cool. Well, if you would want to know more about this, I actually made like a series of videos a while back that are like an in-depth introduction to async IO. So I encourage you to do so. It shows off async IO as this framework that allows Python to be high performance enough for production application. And in fact, HDB, the database, is written in Python, and it is written using async IO, and it is high performant. So back to MapReduce. Our synthetic use case today will just deal with some time series data. So there's going to be some pandas data frames that have datetime objects in one column and some numbers in a second column. To just spice things up, sometimes the numbers are going to be nans, so not a numbers, because something went wrong in kind of gathering the data, and so on. So it's a synthetic use case. I don't really have a great real-world example for you there, but it'll enable us to see all the moving parts that we need to kind of analyze and improve so that the thing is fast. But at least it is an example. My mind works best with examples, so we will be able to focus on the processing part. Later on, you can add on a server on top of this. You can add more things on top of that. That's fine. Today, we're focusing on the processing bit. And the processing bit is simple, right? We load some data from somewhere, we process it, and we return it. But obviously, if the data is bigger than what you can handle in a single thread, or maybe even on a single machine, what you have to do is you have to split the data somehow, gather the result, and only later return it. So this is what we're going to do. And at first, we're going to have this example with the, kind of serialized processing. Later on, we're going to split and apply some magic. And we're going to see that the second one is 25 times faster. So, spoiler alert. Anyway, I will be showing the code that actually makes all of this happen. And if you're like me, you get easily distracted by things that you see, but you don't quite understand because you're using helper functions that don't behave as you expected. So let's just use one slide and just on that so you can see like, hey, the print is not a print because I wanted the print to be nice and I wanted it to be colorful and I wanted it to show us which process we're in. So we're using rich to essentially just show us, in colors that, oh, this is how much time this thing takes, and this is the process we're in. And then there's a mem usage in the bottom. The only thing it does is it uses trace malloc, which you should use as well, to tell you, oh, the current memory usage is this, and the peak memory usage was that. So yeah, with that out of the way, our main async function, oh, no. We have to make data first. So, of course, like in the real world, what you would have is you would get this data from somewhere. You would just need to know its shape. Here, we're going to generate some. So the easiest way for us to generate it would just be to just create some data frames and put it in a pickle file. So this is what we're doing. Maybe there's a nicer way to do this with NumPy or pandas, you can tell me after, but that still did work. It did take an awful amount of time, but we only had to do this once because it's our big data bundle, so fine. It is 45 gigs big, which is barely enough to fit in my laptop's memory. These are amazing times. We have like laptops with like 64 gigs of RAM. It's like, cool. So I cannot even tell you this is big data. Like, no, it literally fits on my laptop's memory. But it's still a lot, right? And it still takes a lot of time to process this amount of data, even with modern processors. So yeah, okay, let's go with that. So a little more than 45 gigs of pickle file. And ultimately, kind of we will just be using this synthetic data file because it doesn't quite matter. How we're going to process it? With this very elaborate function, right? We're just going to call nonsum on this. It is an example, right? Usually what we want to see here is there is some processing that is really not easily kind of decomposable by you. You just have something you need to call to process the data on. Nonsum, great example. Just to be fair to NumPy, maybe there's some NumPy contributor here, I have to say that NumPy, in many cases, when it's doing its thing on the C side with a large set of data, will still free the GIL. So other threads in your program will be able to do something else while NumPy is crunching numbers. Not always. I'm not sure if in this case, but often enough. So NumPy is super efficient on its own already. But bear in mind, this is just an example that shows us processing that holds off the thread on asyncio from doing anything else. Asyncio, we want to always have, a very short moment of processing so that we can go back to the event loop and ask, do you have anything else for me? Otherwise, you cannot really support all the other request responses or health checks or periodic functions that you have in your application and so on and so on. So this is a good example because you're just running through this nonsum, like actually takes a few seconds. So we will be kind of breaking this down to multiple processes. Yeah. Okay, finally, our main async def. There's not much interesting things that happen here, even though there's a few lines. The most important thing here is that we're using a process pool executor from asyncio. And we can say 1 worker, we can say 100 workers. What we're saying here is we have all this data, right, that is given to us as the input argument, and we are splitting it into batches, and if each of those batches, we are running in an executor, right? So loop.run an executor runs our process function with the slice of data. The slice of data is kind of efficient in NumPy, so cool. And then we're waiting for results with the single await that we have there, so asyncio.wait. And later on, we're just summing up the results, which is this final phase of MapReduce. We're just using our batch results to create a total sum. Done. Well, so we can actually have many workers, we can have one, we can have multiple. So how do we run this entire thing? Like the easiest thing that we can do that fits in a slide will be just this. So we just start trace malloc. So to be able to actually just gather data later on, we need to start it. We load the data from a pickle file, and we use asyncio run to run our main async function. So how does this look like for a single worker? A single worker will take a little under 160 seconds to complete. Cool. 2 billion records, so maybe that's not so bad. But, well, my laptop has more than a single core, so how about we add more workers to this? So we add 4, and suddenly we have 69. Nice. The problem, though, is that I have 10 cores, not 4. So let's introduce more workers and see if it's faster with 10. It's not. And it's weird. Maybe there's some clue on the slide already why it isn't, but it is quite a bit disappointing. And there are a few clues. The first one is that it takes a long time for any worker process to even receive our data. The first worker process waits almost 10 seconds to get anything that it can work with, and the last one waits over a minute to do anything. So the fact that we spawn multiple doesn't really help us at all. They're just idling until they get their data. Why is that? Well, our naive kind of view of the world at this point is that we have this one main process that dispatches data to multiple workers and they do their thing. But in truth, there is a little more subtlety to this. We have to serialize the data first to pass it to a child process, which in turn has to deserialize it. We are using pickle for this. So there's pickling on the brown side and unpickling on the blue side. And the problem there is that there is only one dispatcher. So there can only be one process that does all this pickling of this entire 45 gig data file. And this is obviously an issue. We would have to do something about it. Better yet, if you actually see what is happening, like the example is extremely pathological because it takes 10 seconds to get the data and then 0.81 seconds to compute the result. So obviously, just adding more workers to this only makes matters worse. Like it just makes no sense to operate like this. But we're in fact a little lucky that it serialized itself by mistake, because if it didn't, we would run out of memory. The main process already takes 50 gigs of memory, and if each of the worker processes would really take 4.5 gigs at the same time, well, we would be in trouble on my laptop, right? We would start swapping, and that would be terrible. So what can we do? Well, maybe we can use copy on write. What is that? Well, on Linux at least, there is this system call called fork. So when you have a process and it has its program pointer to like the next instruction that it's going to execute, and it has some data segment in memory, if you say fork, you're creating a child process from the process that you're already on. So naively, what you would do is you would just create a new segment in memory for the program and a new segment for memory for the data, and you would put the pointer somewhere in the child process and start running. The problem with that is that it's pretty slow, because if the process is using a lot of memory, copying this this entire space is pretty, time-consuming. So for fork to be faster, Linux uses a trick where it just observes how the program uses the memory, and as long as it's only reading, we don't really have to copy the parent's memory space. Only if the parent or child mutate any of the data, now we actually have to create their own respective copies. So in theory, that would be an improvement for us. But in practice, it's not, because Python's memory management is such a weird beast that even object reads create memory writes because of our garbage collector. So here, 7 years back or so, I created an issue that's saying like, hey, let's add GC freeze functionality that at the time would really help Instagram to, kind of pre-start their server, freeze some objects so that they will never be mutated by Python's garbage collection, so that copy on write would actually be useful. And it is. But in our case, if we want to ever have more than one data set being loaded to our program, that is obviously not going to help us because, you know, kind of we want to be able to process the data as it comes. So just freezing things, no, not sensible. So how about the per interpreter GIL, or also called sub-interpreters? Honestly, very excited about this. This is awesome, very promising addition to Python. What it does is it allows us to have a single process house multiple isolated interpreters. So they are independent. And independent is the key word here. They don't have any data sharing. Objects of one interpreter are invisible to the other interpreter. So sadly, there is no current way to share data there. Eric spent a lot of time implementing this because it was really tricky to make sure that one interpreter does not step on another's toes in the same process. So it's an awesome achievement, but we still have some work there in the future to actually make data sharing kind of automatic or easy to use from this thing. And again, that's a feature of 3.12, so by the time you get to it, this is going to be a while. So what we're left with is shared memory, the main topic of today's talk, in fact. Amazingly, this is a feature of operating systems all around. Like, it's supported by Windows, it's supported by macOS. Obviously, it works on Linux. So I'm kind of surprised it's not more popular. So we're going to be using shared memory now in our program. And there's changes that we have to make. There are lines of code that we have to add. But fundamentally, it's not entirely that complicated. What we're going to be doing is we're going to be creating a shared memory manager. And with that shared memory manager comes a shared memory segment that we create. How big should it be? Well, let's say it's as big as our data set at the moment. Like, if you had a production application, you would probably want it to be bigger, like with some padding, so that if there's a bigger request later on, you can still fit it. Like, at our case, like, we can just literally just say same size of bytes as the data that we already got. And then we can use NumPy's magic powers, which is to create an array mapped to an existing memory buffer, which we do here, and then we just copy our pickle to the shared memory. It is a little annoying. I have to copy here, and it's not optimal. Ideally, maybe pickle could learn to write to shared memory directly or something, or we could use a different deserialization method that writes to the shared memory directly. But it is what it is currently. It's an example. Just have in mind that, you know, annoyingly, we have to copy at least once. But this once is happening on the main service once, and then we don't have to do anything ever again. So with this in mind, with the old situation, we had our main function accept the data segment, and then we batched it as we were passing arguments to the process functions in the executor. We're going to be changing this right now because we don't want to actually pass data to the process function. Instead, what we want to do is we want to just be able to use the shared memory from the workers as well. So now we will be only passing tiny metadata, right? So the process function will accept the shared memory segment's name, the shape of the data, so that you know, we can use it directly with NumPy on the worker side. The dtype, so NumPy knows how big each element in the list is, and some windowing. So, you know, it's going to be an offset and a batch size that each worker has to know about. Because now we have this huge memory segment that we share, and we have to tell each worker that you deal with this part, whereas the other worker will deal with this part, and so on, and only after we're going to sum up the results out of all of those. So cool. So now we already pass some metadata to the process function. We need to modify the process function. So before it was nice and tiny. Now it's going to be a little less nice and tiny. But if you look closely, like half of it is my blown out, you know, signature, right? Because there's just more arguments, and I like type annotations. So yeah, Other than that, we just create the memory segment back with the name that we have provided. And again, just recreate the array from an existing buffer. We don't need to copy to it anymore. We just use whatever is already there. And we can actually use the non-sum again, but now we have to use our window, so our offset and the batch size to just process the sum for the segment that we want. And essentially, that's it. So now, when we have all this, see, there is no data passed to the process anymore, only tiny metadata, which is awesome because the situation before was that the serialization and deserialization took a long time. This is not going away. We're still serializing and deserializing, only now we're doing this on tiny pieces of information, right? We just tell to the worker process, there's like 3 ints and, kind of 1 string. Like, it's very quick for Python to serialize those tiny pieces of information. But now, with those metadata, we are able to access the shared memory block directly from every worker. So how fast is it? Boom, 6 seconds. So yeah, like that's literally the 25x improvement that I promised. So let me show you the slide again. Cool, we won. You should be excited. There are some caveats, so kind of. I'm an honest person. I'm going to tell you that not all's well in paradise, but 25x improvement. Anyway, now we actually see that the time to receive the request is essentially, we can just ignore it, right? The first process, the first worker process and the last worker process receive the request essentially at the same time, which is what we wanted. We see that there is a tiny bit of time spent on actually creating the shared memory segment kind of access from the worker, but it's still like what, 40 milliseconds? So like it's also tiny compared to what we had before. So that's great. And then the processing actually happens now like kind of chaotically in parallel, like spawn process 5 is faster than spawn process 9, and spawn process 11 is, yeah, you can see there it's a little chaotic, but they all converge and actually send back a result, which is awesome. And the even nicer thing is that because of how this works right now, the peak memory usage was 5 times slower, but the actual memory usage at the time of sending back is essentially 0. Like, we're not really using any memory anymore. Like, it's just this one sum number, so it's awesome. But if you look at the top of the slide, you will see a new 25 seconds spent on actually copying the pickle to the shared memory segment. And this is, again, something that would be cool if Pickle could do it, or if we had a different serialization method that just wrote to shared memory directly, so we could skip this. But I'll just leave this as homework to you. Sensible contribution to CPython. Like, we're living in those awesome times where, like, what should I work on? Like, great example. So anyway, even if you're like, this is not solvable, we will always be stuck with this, if you still combine those two numbers, it's still 5 times faster than the serialized version, so it's still worth it. In any case, shared memory, pretty awesome, because there's no serialization overhead, true parallel access to shared data, and less overall memory consumption. On the flip side, as you could see, there was more code. We actually had to handle this shared memory manager and the shared memory names. We had to pass those and, kind of fight with the offsets and everything. So there's definitely more code. But more importantly, there is a disadvantage that there's true parallel access to shared data. I realized that I also listed this as an advantage, but if you actually mutate the shared data from one of the processes, you might end up in a situation where the data structure is half complete, half mutated. It's not finished, done doing its thing, and another process actually concurrently, actually in parallel, is accessing this unfinished data structure and crashes. So the GIL kind of makes sense, right? But if you really want true parallelism, is what you're getting. So if you need to synchronize things to make sure that you're not stepping on each other's toes when you're mutating shared data, you need to do this explicitly. And there is a nice helper in the shared memory support in multiprocessing that can help you. And to show this, let's go and try out Windows, because I promised you that shared memory works there too. And in fact, starting yesterday, when I actually reminded Steve Dower to do it, the Windows Store version of Python is now 3.11 as well. So if you download Python from the Windows Store, you're going to get 3.11 at the moment. So cool. If you do and start it on PowerShell, you can now create a shared memory segment, but not a raw one, but one called a shareable list. And inside the shareable list, you can put strings, you can put bytes, you can put numbers, nuns, and booleans. And that's essentially it. You can do a lot with that too, right? Like, I mean, it's a way for processes to communicate, so pretty cool. And another process could actually, using that same name of a memory segment, could read the list back. So pretty cool. They can do things. They can like send timestamps. Oh no, they cannot send timestamps because timestamps are arbitrary Python objects, and those are not supported. With many types, what you can do is you can find some way to serialize them to primitive types, in which case you can share them again. Like if you ever use JSON, you know the story. So here we can, for example, use just the timestamp method on the datetime object. Just put it in the list and read it back, recreate the datetime object on the other end. Boom, it's the same one. Only the issue is that now you are back in the serialization, deserialization business. So if you're going to be doing this a lot, it's going to slow you down, right? So you have to know what you're dealing with. Most of the time, it just makes sense to use primitive types if you're using this. But when you are, the nice thing is that mutations of the shareable list are atomic. So you're never going to end up in a situation where an object is half copied there and half not. Like that's not going to happen to you, which is great in terms of consistency. In the NumPy example that we used before, we just mapped a NumPy array over arbitrary segment of memory. So if there are any changes that change the shape of it and the other side doesn't know about it, you're going to get a crash. Here, less likely. OK, so let's show another example. Looks the same, but it's not, because now it's Windows Subsystem for Linux. So we cover Linux with Windows, I know. It's a little disappointing, but we don't have time. So, I know. One of you would ask me this, like, dude, all of what you've shown can be just used with multiprocessing. You don't need to use asyncio for this. So why do you always put type annotations in your slides? No, I mean asyncio in your slides. No, like asyncio is awesome because if you have your processing there, you can add so many more things on top of this, like a health check. You can add progress monitoring. You can embed whatever you put here in a server that you already have for a different purpose. So like asyncio composes like really nicely in this sort of way that, kind of with fast API and whatnot, like it's also super easy to use. So like there is really no excuse because it is the way to write Python in ways that is as fast as Go. Like, so, kind of if you really want fast servers, that's how you get to those. So I would really kind of suggest you look at it. Also because if you are really doing things that are, dealing with multiple things at once, so concurrency, however you're doing them, with threads or with asyncio or gevent. No, don't use gevent. But, there are multiple ways to do this. You're going to have to handle errors. And now we can handle errors in asyncio in a really elegant way. So what I kind of did before is I showed you the happy case where everything is fine and there are no try excepts because nothing ever fails. And it's a nice story, and I could finish my talk right now and you would think, this is so awesome. And then you would saw some exceptions and like, Łukasz, you liar. So let's synthesize a failure in our process function by saying, it'll say, oops, I failed whenever it's spawn process 1 or spawn process 11, right? Whatever. It's stupid, but we just need an exception to be raised. So, OK, that's arbitrary enough. And if we run this in our happy case code, what we're going to get is an exception. We accepted that. Like, I don't expect you to be able to read this. It's just there's an exception, right? Like, there's a value error. But what you should also notice is that, oh, it's the main process that totally crashed because just one worker crashed. That kind of sucks. Like, we should do something about it. So what you can do is you can wrap this for loop here around with try except and say, well, if we try to get a result and there's an exception instead, we're going to catch it. Fine, but you're going to get one exception from the batch, and then you're in the except clause, and you're done. Like, this is the most thing that you can learn from it. So maybe you can observe all the exceptions by hand in the for loop, and then you have to gather them somewhere, and then you have to do something manually with them. It's kind of annoying. But most importantly, and if I'm honest with you, the original reason why there are no try excepts here is that I simply forgot. Because it's really easy to just forget when you're excited about getting something running, that like, let's just deal with this, let's just make it run. And then it runs and you're happy, you go away, and now it's the on-call's problem if it crashes at 3 a.m. So now, let's not do that. Like, instead now, in 3.11, you can use task groups. If you use task groups, those are async with asyncio task group as TG. You have a block in which there are no awaits. What the hell? Oh, because what is happening now is we are creating tasks inside the task group. And the task group guarantees that by the time you leave the task group, right? So you leave the async with block, all the tasks are done. So there are not going to be any runaway tasks. You'll know that everything just finished. And what if there's an exception? What if there's many? Because those are multiple processes that are literally running in parallel. So there can be many exceptions. In this case, we're going to cancel everything else by default. You don't have to do anything so that there are no runaway tasks. Everything is complete when we exit the async with block, which is great. So if you don't actually add any other try excepts, you're still going to get an exception, but you can see it's a little different. Because now we have an exception group. So if there will be many exceptions, we already have all of them grouped for us, so we can actually see all of them at once. But better yet, if we simply use Python 3.11's except star with the value error there, we can already react to those exceptions as they happen. We also ignore the canceled and exception tasks, as I said before, just so that we can actually report a result. And with those changes, we get colors now. Thanks, Rich. So yeah, this is actually cool in the sense that even if you forgot about the try except, even if you forgot about the canceled and exception tasks, if you just defaulted to using task groups, it would always tell you right away that something went wrong. There's an exception group. Right? And you would not have any tasks that are lingering, making it harder for you to shut down your application with Control-C or however else. Defaulting to task groups really changes how I think about asyncio because it makes it much easier to structure your code correctly. Everything that is within the async with will be dealt with by the time we're done with the async with. You can obviously even put awaits there, and amazingly, asyncio makes it work, that it'll only cancel the part that is inside the block, which isn't a scope in Python. So it's a little tricky how they did that, but it's amazing. So I'm really happy about task groups. It's on its own a reason to use asyncio over just dealing with threads, which give you none of those niceties. So anyway, oops, I failed, and we can move on to, yeah, I actually made an entire 45-minute talk only about except star and exception group. So if you're like, sounds cool, but he really didn't explain this well, you can give me another chance, and if that still failed, then I'm sorry, you can just leave me like, a thumbs down on YouTube. So yeah, again, what about subinterpreters? Can we actually use them anyway? No. And the reason why not is that there is no executor in asyncio yet that would allow us to use subinterpreters magically as we have thread and process pool executors. But again, homework. Like, there's a full room of people here. Like, that might be your contribution. So I invite you to actually play with Python now. Like, these are really fun times to find out new ways to use it. My name is Łukasz Langa. I'm really happy to be here. Thanks for the opportunity to speak. I'm not taking questions, but I'm here the entire event, so you can ask me questions in person. Thank you.